Okay. Are there any questions?
Hello there. I previously worked on transfer learning algorithms for universal induction using stochastic languages. So what I want to ask you is, what do you think are the most important open problems, preferably algorithmic problems, regarding stochastic inference?
Whose questions do?
But anyone can answer, whoever would like to.
Try to use this for now. I'll look for the other camera, for the other microphone.
Who would like to answer? Somebody might.
Could you repeat the question so that we have a bit of time to decide who has to?
Well, yeah. What do you think are the most important open problems in stochastic probabilistic inference?
So one of the big traditional problems in stochastic inference has been the lifting problem. But people seem to have a pretty good handle on that at this point. I'm actually more concerned in some of the learning issues than the inference issues in them. I think those are bigger problems. How one does structure inference or structure learning in these kinds of things. I think we have pretty good ideas about how to do the parameter learning and all that kind of thing in stochastic representations. I think we know a lot less, though there's certainly been some work, on how you effectively learn these structures. Let's see if anyone else has answers.
Okay, that may actually be later. From our perspective, there is more than one level. There's many different levels of learning. So one thing is learning physical action of like a robot, which might be something more stochastical, but there may be linguistic learning, there may be learning of about social interaction, which may, for example, involve plan recognition, which has nothing to do at all with stochastics. Particularly if you try to look at one-shot learning from a single interaction that you observe. So I would see stochastical learning as only one of like 5 or 10 different ways of learning, and I'm not sufficiently familiar with stochastic learning to provide any specific answer to that question, but there are more levels than just stochastic.
Thank you.
Thanks.
Howdy. Many of you discussed emotion. Some of you discussed emotion in your models. And I was wondering if you could pick apart emotion a little bit. Damasio, amongst others in cognitive science, makes a distinction between emotions and feelings, with emotions representing physiological attributes such as heart rate, hormonal flow, flight or flight preparation, etc., while feelings are described as the central nervous system / cognitive states. And for example, in memory, if you bring, and those are the feeling side, and the feelings are what are stored in long-term memory. So an ordinary retrieval of an episode may retrieve the feelings associated with that, which are not necessarily going to trigger the emotions. However, i.e. the physiological manifestations, while in some dysfunctional times like PTSD, may well be the case that its feelings cause a recurrence of the emotions. Anyway, it's wondering if the distinction between emotions and feelings are useful in the kinds of models any of you are thinking about.
So I guess I'm one of the three that's actually done something on emotion modeling. I find that terminology confusing, frankly. Partly we haven't gotten that far, but there is a distinction between the current state and your memory of that state and what's re-evoked by the recollection of that memory. There's also low-level and high-level appraisals. To some extent, emotions tend to be higher-level appraisals that are combinations of lower-level ones. Those are terminology that I can make sense of more than this distinction between emotions and feelings. So that's not a direction I tend to go.
Yeah, this is a question for probably all of you. I mean, one of the things that has always interested me in the SOAR, ACT-R, and all the work in that direction has been the emphasis on architectures more than on learning algorithms, which, you know, is sort of against the mainstream of all the recent work on machine learning, where there's architecture of a neural network or something, but it's architecture at a lower level aimed at guiding a learning process of some very specific nature rather than the broader cognitive architecture. So now we've had some discussions of broader cognitive architecture. So I wonder what you guys think about, I mean, where are the bottlenecks that you see in getting from your work toward more and more intelligent systems? Are they more in, you know, getting stronger, more powerful, more scalable learning algorithms, broadly speaking, to work within your architectures? Or are they in, you know, fleshing out the architectures and better understanding what the components are, what kind of information do they send to each other, and so forth? I mean, where do you think the hard part lies ahead, or is it everywhere?
I don't know if I'd say everywhere, but at least from what I've been doing, there are hard parts and parts to be done in both of those. So we're looking, for example, at whether our graphical models with gradient descent learning can do the same kinds of things deep learning does. And so we're looking carefully at that work as well as the mapping of that onto graphical models. I think there's a lot more we have to do in learning. I said, I think the biggest gap we have right now, this actually came out of looking at your summary article, Ben, and looking at the strengths and weaknesses of the 4 paradigms and stuff. Our biggest weakness right now is structured learning. So there's something big we have to do there that we haven't done. But I also believe that all of the approaches that start with just graphs, or any of the approaches that start with babies, without a fully fleshed out architecture, they can't get very far. They can do very nice, pieces in isolation, because they learn that, but they can't put all the pieces together. That's what the architecture is about. How do you get all the pieces to work together? And that's not just a single graph or a single network that you're learning about from experiencing the environment. So I really think it requires both, and I don't think we solved either problem yet.
Okay. I actually would partially object to what you said initially, that machine learning always focused on the algorithms. Like, at least over the last maybe 12 to 18 months, there's been things such as the misnomer of 2014, neural Turing machines, which actually should be called neural von Neumann machines. So people try to actually get machine learning approaches into architecture. Still, they're far from being a cognitive architecture, granted. But people are slowly starting to try to actually get more mechanistic approaches. And with respect to challenges, I, at least from the perspective of what I presented here, would see is actually getting the translations right. So if you want to say, is it components or is it communication, I would actually say it's more on the communication across formal boundaries and modalities. So whilst we're pretty good at doing all the, say, statistic-driven learning, and whilst, for example, we are pretty good at doing rule-based reasoning with symbolic architectures, we still didn't figure, although we have the proofs that in theory they should be equivalent, we still didn't figure how to do one in the other paradigm. So I guess that it would help a lot if we actually would either know how to do efficient learning on a cognitivist or mental level, so on a symbolic paradigm, or if we actually, okay, partially we are beyond the propositional fixation, but if we could really push in terms of controlled reasoning beyond the boundaries of simple hand-built examples in neural networks. So I think it's more of a translational problem which would break probably several boundaries, then actually getting yet another component, do yet another functionality.
The actual hard problem is to present a new cognitive architecture in 10 slides. So that's why I skipped anything about learning, because it's just so many more concepts, and particularly when when I was talking about more than 10 different levels of models, then it each needs its own specific learning mechanisms. Then this was just out of this discussion. Maybe discuss it on Saturday. What I want to contribute here is that hand coding as a kind of learning is obviously dead. So any cognitive architecture or similar that relies on manually coding knowledge into the system is dead, is since 30 years proven to be not working. I think that's, maybe some people may.
Do you include,
because of the amount of knowledge. Excuse me.
We have to talk about the notion of proof, but okay.
Agreed. I'm an engineer, there's no proof. If it works, it's a proof. If it doesn't work, well, if it doesn't work, 30 years. So anyway, the point is learning, but learning in an effective way. And what we propose, there's one contribution here to the learning part, is we propose plan recognition as the learning paradigm, because it acts on a very high level on the social, basically, or three-dimensional observation level, and the predictive power of the system should be able to predict the future steps of what somebody is doing, basically the plan he wants to execute in terms of social. And if something of this prediction doesn't work, then it needs to be an inquiring process. This requires a bootstrap process, because just getting that far requires a lot of capabilities, practical inference power, plans, plan libraries and whatever. So there is this bootstrap problem, which is very clear and has become clear from the initial implementation intents already. So yeah, that's the reason not to present learning, is because it's so much about it.
right, well what you're saying is you think the most critical problem is sort of the combination of architecture and learning algorithm to allow bootstrap learning of plans.
If you got high-level learning, you need to have the underlying processing power to make sense of the inputs on the specific level. So otherwise, you'll only have like very flat, low-level.
It's kind of the same thing Jürgen said at the end of his talk when I asked what he thought was the hardest problem facing him in making a capuchin monkey mind out of RNNs. I mean, he said plan learning was the hardest problem.
Actually, I believe it's more, he's got more representation problem there, because he needs to represent like a planning state space using flat one-bit status neurons, I don't know, code complex states with relatively simple mechanisms. So this is a very specific problem, I guess, on neural networks, while being more a symbolic guy there, at least in terms of the representation. I think the problems are different there. Most of our levels would need statistical neural network learning algorithms on each level, but this would be then several ones. But it really, to me, this is pluggable. This is, as an engineer, I don't really care whether the learning algorithm is the statistical one or a neural one. But there's, on each of these levels, there's...
I'll let Paul defend rule bases, but first I want to push back on your statement that if it didn't yield results in 30 years, it's no good. I mean, I don't really like hand-coded rule bases that much myself, but I mean, you could have said before the Wright brothers, like winged craft will never fly. There's been hundreds of years of efforts, and they always fall down, right? So I mean, 30 years is not that long in human history, because research is slow. So I don't think that's a good line of argument. Personally, whatever are the merits of hand-coded rule bases.
Yeah, and Site made a release, so.
Yeah.
No more
but I'm curious for Paul's rebuttal on that topic.
Yeah, again, time isn't always the important thing, but it depends on what you're claiming they failed at. So as an engineer, you should appreciate any number of very successful engineered systems have been built in that fashion. And there are increasing knowledge bases available. Some of them learned from stuff on the web, some of them put together by hand, that systems can incorporate and make use of. Ken Forbes's companion system, for example, incorporates OpenSite as a knowledge source in his thing. And that reflects large amounts of hand-encoded knowledge. So I'm not quite sure what the notion of failure is. If the notion is we're not going to get to full general intelligence just by programming rules by hand, I would agree with that. But I don't think anyone is claiming, not at this point, even with SOAR, the assumption was almost all the rules had to be learned. The question was, what had to be there first before you could learn all of those rules? There's a separate question of whether it's rules or something else, or a hybrid between them. But so you have to be careful what claim you're making and what failure claim you're making.
Correct, yeah, I agree.
I just got a signal